All right, so good afternoon. My name is Zulliet Cabrera Gomez, and this summer, my research mentor and I had the opportunity to investigate the impacts of metasomatism on Colorado Plateau's lower crustal density, providing us with insights from xenoliths from the Moses Rock and the Mule Ear diatremes of the Navajo volcanic field, located within the Gopat. I threw a lot of words at you, so let's break it down. Metasomatism is the chemical alteration of a rock through its processes with hydrothermal fluids. This just refers to the change in a rock's chemistry with the addition of water to the mix. A xenolith is a rock fragment enveloped in a larger rock throughout the solidification of that larger rock. So what this means, well, let me give you an example. So imagine you're in Hawaii and you see a running lava flow. Out of nowhere, a rock breaks off from a cliff in the distance and it passes you, but it gets caught in that lava flow. What's happening is that rock that tumbled down will be enveloped in the lava where it will solidify. And that is how we get a xenolith. And a diatreme is a funnel-shaped volcanic pipe associated with gas-rich eruptions. And this is where our xenoliths were once located. And the diagram to the right shows us what a diatreme looks like. And you can also see the location of where the xenoliths are within the volcanic pipe. Okay, so let me introduce a little bit of background. The Colorado Plateau is a landform event that was formed through flat slab subduction roughly 80 million years ago within the Laramide orogeny. And this subduction event provides us with evidence for lithospheric hydration. And the way we approached this was by examining pre and post hydration assemblages through the use of density models. Now, why are we looking at this? Well, the reason we are is that, the reason we are is because there is 2 kilometers worth of surface uplift that cannot be explained through the shortening of the Laramide alone. And we'll take a closer look at the effect of hydration on lower crustal density. And in the image, you can see that there's a huge space left from the subduction event, and it's quite large. Okay. Let's go. This image shows us where our samples were located. And we have a total of 5 samples located between the Moses Rock and the Mule Ear diatreme. 2 xenoliths were taken from the Moses Rock as well as the Mule Ear. And the Moses Rock produced 2 thin sections while the Mule Ear diatreme produced 3 thin sections. Here you see the thin sections that my mentor and I were looking at for the entirety of the summer. And notice how there's a variety of textures throughout each thin section. This tells us something about the lithology. Well, and this just tells us that there's different lithologies within the samples. 005 is a garnet amphibolite. A 006 is a xenolith that was broken into 2 thin sections with a garnet biotite schist lithology. 008 is an altered diorite, and 009 is a garnet pyroxene granulite. Yeah. These samples were then taken for a quantitative evaluation of materials by scanning electron microscopy, otherwise known as a ChemScan. And the ChemScan provides us with Modal Mineralogy, which is collected from the Colorado School of Mines. Our samples were then underwent an electron probe microanalysis, otherwise known as an EPMA. And a diagram of this machine is shown to the right of this, and it determines composition on a small spot of a thin section with a high energy beam. Then the Abers and Hacker 2016 calculation model was used to generate density and temperature and pressure. And lastly, density models were then developed into pre and post hydration models. Okay, here we have an example of what a ChemScan and an EPMA figure would look like. And it's taken from the M72E006A sample. The ChemScan to our left is a colorful mineral map where we have each color representing a different type of mineral. And the ChemScan provides us with a bulk modal analysis of the minerals present. The EPMA, which is to the right, shows us a quantitative elemental analysis at very small spot sizes within the thin sections, and it's through the use of the high energy beam. And the figure shows us the 006A thin section with 3 boxes highlighted, and each box is zoomed into a grayscale X-ray map of those boxes. And within those boxes, within those grayscale X-ray maps, there are EPMA data targets shown in yellow, which are tiny, and these which would be accumulated into the Abers and Hacker model. Now, this information, both ChemScan and EPMA, was collected for each sample, and we were able to construct modal mineralogies of pre and post hydration, which can be seen here in this model. Here we see the minerals present throughout the thin sections, right? Each individual one. Post-alteration refers to what we see in the present day. So our pre-alteration is an extreme case of an inferred mineral calculation before any hydration occurred, before any water was included. And you can see in the box outline in red, the column with pre-hydration is completely blank, which is this area. And this is because we redistributed the chemistry into anhydrous minerals, which are minerals that don't have any water, into the chemical formula. And in doing so, we impacted the density, which can be seen here in this slide. Here we are presented with density models modeled with 3 axes: the depth, density, and temperature. For each graph, the solid line represents post-alteration and the dashed line represents pre-alteration. So each graph has this solid line towards the left of the graph, like for all of them. And looking at the density scale, we can see that all post-alterations are less dense than their pre-alteration. And the top row shows the most change in density, and this can be seen due to how far apart the pre-alteration and post-alteration lines are. While the bottom row shows us the least the least change in density, which can be seen by how close they are as well. Yes, so let's get a little deeper into this. One interesting finding that we observed is that the 006A and 006B are samples from the same xenolith, a garnet biotite schist, but here in this graph where they are plotted together, they exhibit different densities, which you can see here, where in the green line and the blue line. These samples show the most change in density with a 44 kilogram per cubic meter difference. But if we compare it to a sample with the sample on the bottom, 008, we see that the garnet pyroxene granulite has a much lower change in density of about 10 kilograms per cubic meter. And we come to ask ourselves, why do we see these changes? Well, to answer that question, we first have to ask this one. Are these lithologies representative of the lower crust? And being as our sample data comes from 2 locations of the Navajo volcanic field in the Colorado Plateau, most of these xenoliths are much more dense compared to the modeled density lithologies in the Connie and Silverstone 99 paper. And in this paper, they do not include a garnet biotite schist in their lower crustal lithology model, which could be either because of sampling bias or they could simply not have included it. And in the figures to our right, we see sample 005 and 006. 005 on the top shows obvious alteration where plagioclase is altered to biotite, and clinopyroxene, that's the right word, is being altered into amphibole. But in the bottom, we see that the 006 sample, where we don't see, in the bottom image, we have a 006 sample where we don't see the obvious textures. Rather, large grained unaltered plagioclase with biotite, with albite twinning is preserved. This is different from this, basically. We come to the realization that sample 006 may not be from the lower crust, or it could have not been affected by the same change in alteration as 005. So the model and hydrous pre-alteration version we made is probably not realistic. Depending on degree of alteration and whether hydrous minerals are primary or secondary, the density change with hydration could be smaller or larger. And to answer our previous question, we don't have enough xenoliths within this study to accurately represent the lithologies. Generally speaking, we aren't getting the whole picture based on these 5 samples alone. In conclusion, minerals react differently to hydration because of the cation redistribution of minerals modes depend on post-hydration assemblages. And big things often have small beginnings, and the evidence for this is the density change. So hydration on a scale model is quite minuscule, but on a larger scale, it's quite big. And again, we don't have enough xenoliths within the study to accurately represent the lithologies, but the 2 kilometer worth of uplift can be at least partially explained through hydration. And I would like to acknowledge my mentor, Dr. Ellen Alexander, for helping me throughout this whole RESESS internship, as well as the territory where our research was taken by the people of the Western Apache, as well as the National Science Foundation. And everyone who showed up today, thank you so much for supporting. And if there are any questions, I am free to answer.
Great job, Zulliet. Okay, you can unmute yourself if you have any questions and raise your hand, or you may type them in the chat.
Zulliet, I have a question.
Yeah.
Can you go back to the slide with the densities?
With the what?
The plots where you show densities before and after hydration. Yeah. Mm-hmm. Here. Can you explain maybe why the bottom right one is the only one that has higher density post alteration?
Wow, you are absolutely correct. Well, I'm gonna be honest with you. I think my eyes deceived me. I really thought it was the other way around. Oh my God, and my mentor even told me that. Oh wow, and it just went over my head. Well, let's see. I know that my mentor said, oh, I cannot answer this question right now as I am a little thrown off because I did not see this correctly. Wow, that's wild. But I will have to get back to you on that one. Juan?
Yes, so Philip was asking the same question I had, so fair enough that you're not sure about that. So I was going to follow that up with a question on, you said that the 2 kilometers of surface uplift could at least partially be explained by hydration. Were you able in this project to actually do any kind of modeling to determine how much, if you were to assume these particular lithologies went over a given volume, how much of that 2 kilometers you might be able to attribute to hydration?
I don't think so. I understand your question, but I don't think that the work that I've done does pinpoint that specific type of location. But that would be cool, honestly, to actually be able to pinpoint. That's interesting. That's probably for future work.
Fair enough. Thanks.
And yes, Raquel.
On that note, I wanted to know what this experience, like doing research, like what kind of new questions about earth science or earth materials are you now curious about?
Ooh, good question. I guess I'm more into the mechanics of the science. So like I like the machinery of it all, and like looking at thin sections and looking at all that. And I guess my question just rises from, if the Colorado Plateau is showing hydration, and there has been some studies on that, is there any place on our Earth where there is a similar aspect to this, and how does it similar or differ to the Colorado Plateau? Really good question though. Really cool.
Thank you. Great job.
Good job, Zuli. There's one question in the chat from Raylan. What was your favorite part of your internship experience?
Oh, my favorite part. I really liked, to everyone here, I'm a returning RESESS intern, and last year it was online. So the fact that we were able to go to Colorado this time around was really fun, and being able to actually see, again, like the machinery. I really like the microscopes, and just being there and talking to my mentor like one-on-one is really cool, and makes you understand more of the science behind it. And it's all basically my favorite part was Colorado.